Hi everyone, welcome back to CHE 101, and today's topic will be on branching pipes under momentum transfer. This is Clarice Halago, and I will be the one to discuss today's topic. Today's discussion will be quite short, so presented here on the slide is the outline for today. So here we have the types of networks, followed by a sample problem on parallel pipes. There are two general types of pipe networks, pipes in parallel and pipes in series. Let us now dive deeper into each of these types. The first one is pipes in parallel. This is a setup wherein multiple pipes branch out from a common inlet and merge back at a common outlet, as shown on the diagram. So in this case, we have three branches labeled 1, 2, 3, all carrying flow in parallel paths. One of the key things to remember about parallel pipes is that a total volume flow rate is simply the sum of the individual flow rates in each branch. This is given by the formula Q total is equal to Q1 plus Q2 plus Q3. This makes sense because the fluid entering the system has to be distributed among the available paths. So if we know the flow in each branch, we can easily determine the total flow through the network and vice versa. Another important characteristic of parallel pipes is that the pressure loss across each branch is the same. This is shown by the formula shown on the slide. This happens because all branches connect to the same two points A and B, meaning that the pressure drop must be equal across each path. The pressure drop is highlighted by the given formula shown on the slide. Using mechanical energy balance, we express the pressure drop in terms of forces. By dividing pressure loss by the fluid density, we can relate it to the sum of the forces acting in each branch, as shown on the slide. Since we know that the pressure loss is the same across all branches, the sum of the forces must also be equal. This is emphasized by the formula shown on the screen. So the summation of forces in pipe 1 is equal to that in pipe 2 and pipe 3. This is a crucial relationship that helps us analyze the flow distribution in a parallel pipe system. Let us now move on to another type of pipe network, pipes in series. Unlike parallel pipes where the flow splits into multiple paths, here the fluid moves through each pipe sequentially, one after the other. So as you can see, the fluid flows through three connected sections labeled 1, 2, and 3 all in a single path. One key characteristic of pipes in series is that the volume flow rate remains constant throughout the entire system. Here we have Q equals Q1, Q2 equal to Q3. This makes sense because there is only one continuous path, meaning the same amount of fluid must pass through each section per unit time. Another important concept in series pipe networks is that a total head loss or energy loss due to friction is the sum of the losses in each section. So here we have the total forces is equal to force 1, force 2, and force 3. This means that as the fluid moves through each pipe section, it experiences additional resistance, increasing the total pressure drop across the system. That's all for the concepts. With that, let's proceed to a sample problem. A pipeline with a flow rate of 1,350 gallons per minute is split into two parallel pipelines at points A and B. Both pipelines are made of cast iron, with one having an internal diameter of 9 inches and length of 1,575 feet, while the other has an internal diameter of 6 inches and a length of 2,885 feet. Determine the water flow rate in each pipe and that the water temperature is 80 degrees Fahrenheit. Let us now list the given values. So it is mentioned in the problem that the given pipe network is parallel. And so we illustrate that through a similar figure shown on the slide. And then we show that water is entering the pipe at a temperature of 80 degrees Fahrenheit with a volumetric flow rate total of 1,350 gallons per minute. It then separates into two pipes, the first one with a diameter of 9 inches and length with 1,575 feet, and the other with a diameter of 6 inches and length of 2,885 feet, both made using cast iron. Let us now get the properties of water at 80 degrees Fahrenheit. So this is from a cave, Appendix 14, properties of liquid water. So here we see the viscosity and density of the liquid water. Following that, we need to get the friction factor of the material of the pipe, which is cast iron. So here from figure 5.9 from the cave as well, we see that the friction factor of cast iron is 0.00085 feet. So we take note of that and list that with the given values we prepared earlier. So here we have listed all the values that we will be needing to solve the problem. And so we are required to solve for the volumetric flow rate that flows through the first and the second pipe. I have also listed here the following equations that we will be needing to solve the problem. Feel free to pause this video to take note of the formulas. Now we're all set to solve the problem. So let us first convert the given flow rate, 1,350 gallons per minute, to feet cubed per second through the following conversion factors. Since the system is a parallel pipe system, we know that Q total is equal to Q1 plus Q2. Taking note that Q is equal to the surface area multiplied by the volume, or V times S. So we expand the formula as shown on the slide. Simplifying the equation further, so we get an equation for V2 in terms of V1. So we take note of that as equation 1. Furthermore, we know that the force in pipe 1 is equal to the force of pipe 2. So expanding that formula, canceling out like terms, and rearranging to get this equation. We then substitute the values for the lengths and diameters of the two pipes and simplify everything to get this expression for equation 2. Focusing on the first pipe, we solve for the Reynolds number in terms of V1, or the velocity. We then calculate for the friction factor. So we substitute the values to the equation and then notice that we raise both sides to -2 to get an explicit expression for F1. Repeating the same process for the second pipe, we calculate for the second Reynolds number, and then we also calculate for the friction factor in terms of V2. But notice that here we took an additional step and converted V2 in terms of V1. So now we have both friction factors in terms of V1. We then substitute everything to equation 2. So here we have a pretty long equation and we solve for V1. So it's up to you whether you want to simplify this further or not. Solving for V1, we get 5.439 feet per second. And that's substituting that to equation 1, we get V2 is equal to 3.081 feet per second. We then calculate for the volumetric flow rates by multiplying the velocity to the surface area. We get Q1 is equal to 2.403 feet cubed per second, which is also equivalent to 1,078.56 gallons per minute. Q2 is equal to 0.605 feet cubed per second, which is equivalent to 271.54 gallons per minute. So, summarizing all the answers we have with the diagram presented earlier, we see that the Q total is equal to 1,350 gallons per minute. As we wrap up today's discussion, let's quickly summarize what we have learned about pipe networks. When pipes are arranged in parallel, the flow splits into multiple paths. With this, the total flow rate is equal to the sum of the individual flows, and the pressure loss is the same across all branches, and the forces in each branch balance out. This setup is useful when we need to distribute flow efficiently across multiple branches. On the other hand, in series pipe networks, the fluid flows through each section sequentially. With this, the flow rate remains constant throughout the system, and the head loss add up as the fluid moves through each section. So this arrangement is common in systems where pressure gradually decreases along the pipeline. That's all for today. Again, this has been Clarice Alago from Chen Academics. If you have any questions, feel free to reach out to our platforms shown on the slide. Thank you so much for tuning in and see you on the next.